Okay, so second question, or second type of question, is where the energy, an amount of energy is given to you. So there's two types, and we'll look at the first one here. The first type will give you a question, something like this. They'll give you a specific amount of something will be reacted. So they say in this case, we've got, say, 4 moles. So this is our specific amount. And this will be reacted with excess oxygen according to a particular equation. So this is the equation that they've given us over here. And it tells us that we've produced a certain amount of energy. So we can see over here, it says produce a certain amount of energy. And then they ask you, what is the enthalpy of reaction? How do we tackle this? The first thing that we need to be very, very clear on is, what does it mean when they ask you to find the enthalpy of reaction, right? So that brings us to the question, enthalpy of reaction. What does that mean? What enthalpy of reaction means is how much energy, okay, so we know that we've got this equation. So how much energy is absorbed or released when the reaction occurs. Okay, that's fine, right? How much energy is absorbed or released when the reaction occurs. But we come into a little bit of a problem, because let's say I have a situation where I have two fuels. So let's say I have a jug here, and this is a 1 liter jug of petrol. And then over here, I have a 500 ml jug. So 500 ml jug of petrol. Okay, if the petrol burns according to an equation, let's say the petrol burning equation is petrol plus oxygen gas forms carbon dioxide and water, yeah, and also heat. Okay, let's say this is the petrol equation, right? I know that this particular equation has an enthalpy of reaction. So there's an enthalpy of reaction for this particular equation. But the question is, if I have a look at the situation, right? If I go ahead and burn this petrol over here, right? It's going to release a lot of energy. Let's say, just hypothetically speaking, it releases 5,000 units of energy, okay, units of heat energy. If I burn this petrol over here, this is going to be I have half the amount of fuel than I do in the 1 liter jug. So it would make sense that this would produce 2,500 units of energy, okay? But when I come down to this, right? When I come and ask myself, what is the enthalpy of reaction? The definition that we have so far is how much energy is absorbed or released when the reaction occurs. But we realize that if we have different amounts of our fuel, a different amount of energy is going to be released. So how do we deal with this? Because there's only going to be one delta HR value for a particular reaction. So when we have an enthalpy of reaction, the question then becomes like, how much energy is absorbed or released when a particular amount of this fuel is combusted? And how do we think about that? So the way we think about this is like this. Let's say I have this equation over here. So we've got methane plus oxygen forms carbon dioxide and water. And we see that there's the coefficients in front of this is 1 for methane, 2 for oxygen, 1 for carbon dioxide, and 2 for water. So you see the coefficients are the ones just over here. Cool. So if I were to find the delta HR value for this, right? When they ask me to find the delta HR value of this, what they are really asking me to find is how much energy is absorbed or released when what? When 1 mole of methane, so 1 mole of methane reacts with 2 moles of oxygen to form 1 mole of carbon dioxide and 2 moles of water. What does this mean? This means that if, for example, if I had, let's have a look. If I have 1 mole of methane, let's say this box here stores 1 mole of methane. it would release a certain amount of energy, let's say 100 units. Okay? If I had 2 moles of methane, it would release, as we said, 200 units. Okay, so that's quite straightforward. But when we have the enthalpy of reaction, they ask us how much energy is absorbed or released when the reaction occurs, right? But what it really is asking us, so we have to refine this, it's asking us how much energy is absorbed or released when the number of mole as in the correctly balanced equation reacts. So what this means is that when we have the correctly balanced equation here, there are a bunch of coefficients in front of the reactants and the products. When they ask you for the enthalpy of reaction, it is asking you how much energy is absorbed or released when the number of moles of reactants and products as per the correctly balanced equation react. So in this situation, since there's a 1 in front of the methane in our correctly balanced equation and a 2 in front of the oxygen, this is talking about how much energy is released when 1 mole of methane is reacted. So in this case, we've got 100 units, but let me just double check the real value for you. Yep, so the real value is going to be 802.3 kilojoules. So that means that 1 mole of methane, I just Wikipedia'd this, 1 mole of methane releases 802.3 kilojoules of energy. So I know if I had 2 moles of methane, it would release double that, 3 moles would release triple that, etc. But in this particular situation, since the balance equation has a 1 in front of the methane, then the delta HR is asking us how much energy is released when 1 mole of methane reacts according to this equation. So the answer to this would be minus 802.3 kilojoules. Okay, so let's go. Okay, so let's have a look at this equation here. So the question comes back and it says 4 moles of methane reacts with excess oxygen according to this particular equation and produces a bunch of energy. What is the enthalpy of the reaction? So as we mentioned before, enthalpy of reaction means how much energy is absorbed or released when the number of mole of reactant and product that reacts is the same as the coefficients in the correctly balanced equation. So the coefficients in the correctly balanced equation are 2 for ethane, 7 for oxygen, 4 for carbon dioxide, and 6 for water. So enthalpy of reaction, when they ask us for the enthalpy of reaction, what they're asking us for is how much energy is absorbed or released when what? When 2 moles of ethane react with 7 moles of oxygen to form 4 moles of carbon dioxide and 6 moles of water. That's what the question is asking us. Alright, so that's what the question's really asking us here. Okay, how much energy is absorbed or released when 2 moles of ethane react? So over here, what have they given us? They've given us some information. The information is what? The information is that 4 moles of ethane will produce how much energy? 6,400 kilojoules. 6400 kilojoules. What we want to know when they ask us the enthalpy of reaction is because the correctly balanced equation has a 2 in front of ethane, it's asking us how much energy is released when 2 moles of ethane react. So 2 moles of ethane are going to produce what? It's going to produce half of this, of course. So that's going to be 3,200 kilojoules. And since the question says when ethane reacts with oxygen, it produces energy, that means this must be an exothermic reaction. Therefore, the delta HI is going to be an exothermic reaction, so we're going to have a negative in front of the number, and it's going to be negative 3,200 kilojoules per mole. So you might be asking, what does this per mole kind of deal represent? In the context of enthalpy of reaction, it is basically represents nothing. You just use it because that's the tradition, okay? All right, so let's have a look at the other type of question that they'll give you in terms of this. So they'll ask you a question like this: determine the enthalpy of reaction at SLC for the complete combustion of butane. So how do we do this? Complete combustion of butane, first of all, let's get the balanced equation. So the balanced equation will be what? We know it's complete combustion, so it's going to be butane plus oxygen, and since it's complete combustion, it's going to be carbon dioxide and water. Okay, and remember the mnemonic CHO, so we balance carbons first, so that's 4 carbons, hydrogen second, so that's 10 hydrogens on the left, and then we've got 2 here, so multiply this by 5, and then oxygen, so we've got 8 oxygens on here, and 5 oxygens here, so there's total 13 oxygens on the right. So what we'll do is we'll write 13 on 2 here, because 13, if you do O2 times half, it gives you just 1 oxygen, and you multiply that by 13, it gives you 13 oxygens. So then we can multiply this by 2 to get the balanced equation. So what we get is 2 butanes plus 13 oxygens forms 8 carbon dioxide plus 10 waters. And since this is at standard laboratory conditions, what this means is that water is going to be in a liquid form, gas is in carbon dioxide is in gaseous form, oxygen is in gaseous form, and butane is also, right now, I think, let's have a look what butane says, it's in a gaseous form as well. Cool. So standard laboratory conditions, remember, are just 100 kilopascals, which is equal to 1 bar as a pressure, and then temperature of 25 degrees Celsius. So this is the correctly balanced equation that we have to deal with. So when they ask us, what is the enthalpy of reaction? What they're asking us is how much energy is released when 2 moles of butane react with 13 moles of oxygen to form 8 moles of carbon dioxide and 10 moles of water. So how do we go about dealing with this or thinking about this? The second way that we can work out these kinds of questions is that we can go to the chemistry data book, and chemistry data book has the heat of combustion of some common fuels. So we can see that the heat of combustion is basically how much energy is released when 1 mole of a fuel reacts with oxygen, excess oxygen, or when 1 gram of fuel reacts. So here, what we're looking for is we're asking ourselves, 2 moles of butane releases how much energy? Well, we can go over here to the chem data, and we can basically have a look over here at butane. We know butane, equation C4H10, when 1 mole of butane reacts, so molar heat of combustion in kilojoules per mole, 2,880 kilojoules are released. So we know 1 mole of butane will release how much? 2,880 kilojoules. So therefore 2 moles are going to release how much? Well, we can do 2 ways. We can just multiply this number by 2, or we can cross multiply. So I'll just cross multiply just to remind us how we go about doing it. So we'll make this x kilojoules. And then when we write out the 2 ratios like this, we multiply it like this. So 2 times 2,880 will equal x times 1. So I'll just leave the 1 out there. Okay, so x is therefore going to equal what? Let's go and bring up the calculator. So we've got our calculator over here, and we do 2 times 2,880, and that gives us 5,760. So that means over here, we've got what? 5,000, let's bring it up again, 5,760. 5,760 kilojoules. Cool, so we now know that 2 moles of butane are going to release 5,760 kilojoules. So what does this make our final answer? The final answer of this is going to be what? The delta HR of this reaction is going to be negative 5,760 kilojoules per mole. Okay, let's just go ahead and get rid of. So yeah, so that's going to be our final answer here. Negative 5,760 kilojoules. Why is it negative? Because we know this is an exothermic reaction, because combustion reactions are always exothermic. Whenever we burn something, energy is released. Why is it 5,760 and not 2,280? Because enthalpy of reaction refers to the number of moles in the correctly balanced equation reacting. So since there's a 2 in the correctly balanced equation, it talks about 2 moles of ethane reacting.